All right, so I just drove you crazy with a bunch of organic chemistry concepts, and I hope it wasn't very difficult, though. We talked about cis, and we talked about trans, and we talked about alkanes, and we talked about alkenes, because all of this is kind of relevant to the lycopene structure, which is what we want in this particular experiment. We also talked about shapes and 3D geometries and why these things are important, and all of that is also the world of organic chemistry. That is what makes it organic chemistry versus something like a general chemistry or an analytical chemistry or an inorganic chemistry type of class. So now we need to kind of turn our focus on the process of chromatography. So we already said that chromatography is really going to separate, and that's what we are trying to do. So you're looking at this and saying, separate what? I thought we already separated. Yeah, you kind of did. You did some extractions. You didn't do some separation, but you did some extractions. So what we did is that we took our tomato paste and you added hexanes at this moment, and hexanes was a organic compound. Hexanes was non-polar, and that solvent went in and it saw that lycopene, which is organic, and that lycopene is non-polar, and they went, ooh, hubba, hubba, hubba. I'm gonna madly fall in love with you, and we're gonna run off and make a baby. So hexanes and lycopene will go off together in the sunset that we call a liquid extraction. So here we get hexanes, we get a colored hexanes because that lycopene, we already said, was red and orangey. So that's going to travel with the lycopene, and we're going to end up with a dark colored solution because of that. The problem, though, is that hexanes cannot make up its mind. And hexanes is going to go into the bar, and it's going to go, hubba, hubba, lycopene, and then it's going to go, hubba, hubba, carotene, and then it's going to go, hubba, hubba, all of you other pigments. Woo, come on, let's party. And then before you know it, hexanes runs off in the sunset with like 15 or 20 people. I mean, polygamy, hello, that's what this is all about. So the issue here is that hexanes plus other stuff is going to be part of this extraction. This is where chromatography is coming in. So now chromatography is going to be like, absolutely not. Hexanes, you're going to settle down. And you're going to pick one thing, and I'm going to help you pick one thing, and you're going to have to kick all the others to the curb because it's time to grow up, right? You need to grow up. You need to have a family. You need to live the American dream and blah, 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 whatever they say. All right, well, if that's the case, we're going to have to figure out how can we separate one component from the entire alphabet soup of other things that have came along with it. So chromatography's purpose here is to help you do that. It is to help separate the pigments, one of which is lycopene, and help you capture the lycopene that we are doing in the lab activity. Okay, so acetone, and sometimes depending on the version of your textbook, PET ether can be used to extract the lycopene. All right. So now you're probably wondering, like, well, why is there a mix? We'll talk about that in a minute. All right. But if you've got like the 3rd edition or the older edition of the manual, then PET ether can be used. It really doesn't matter. It's still organic. And that petroleum ether will still do a great job. If you've got another version of the book, it might actually tell you something different. And if so, you follow that. Hexanes, again, can be one of those. But every time that I've talked about hexanes at this moment, you need to go back and think, oh, well, PET ether could have also been used. So PET ether could have been used. PET ether could have been like, hubba, hubba, come on, lycopene. And PET ether could have been used to be like, hubba, hubba, carotene, let's go party. I mean, the story's the same. And again, it really depends on the edition of the lab manual that you've got. In addition to that, PET ether, like I've said before, is still organic, just like hexanes. PET ether is still non-polar for the most part, just like hexanes. It's not a big issue at all, but it works, and that's kind of the take-home message. So whichever version of the text that you have, keep in mind the process is the same. It does not matter. Okay, so with that said, we are using an extraction solvent. We're pulling out the lycopene through the use of a couple of these solvents. And then maybe at a certain point, acetone can be incorporated as well. Acetone can be incorporated, again, depending on the version of the textbook that you have. If you do have a version that uses acetone, it is not a big deal. Acetone is also organic-y, but acetone has a little bit of polarity that is assigned with it. It actually somewhat helps the job. It brings some more pigmentation along for the ride. It's not going to overcomplicate too much of stuff at all. So just keep that in mind. If you do have the version that's just like hexates, then do it. But if you've got a version that says acetone / pet ether, then that is perfectly okay. Do it. Woohoo! You'll still get the same concept. You'll still get the same results in the very end of this. It's no big deal. Trust me, we've done it both ways. And there's actually many more ways that you could have done it using completely different solvents that would still work, because that's the beauty of organic chemistry, right? If you know how things work, if you know how things play with each other, then it's very easy to substitute one thing for another. Beta carotene is also going to be pulled, though. This is one of the biggest problems that we get when I begin the extraction. So lycopene comes out great, but beta carotene will also come out great. And the reason is that this is the structure of beta carotene. Woo, doozy. Look at that structure. Double, single, double, single, double, single, double, single, cause you trouble. I mean, come on now. Double, single, double, cause you trouble all over the place. This is another conjugated system. Go figure. Because it's conjugated, guess what? My eyeballs can see it, probably, because there's a strong chromophore in place, and it can also show up in things like a UV vis spectrometer, because a chromophore is there. That is why it responds so well to light energy. So this structure is very similar to lycopene. No wonder it will come out with lycopene. With whatever solvent you decide to use, no wonder it happens, because this is what goes on, right? Very similar, and that's why I call this a sister or a brother type of compound to lycopene. If you look down in the bottom corner, that's the structure of lycopene down here at the very bottom. Well, beta carotene, look at this. The difference here are these big bulky things for the most part on the outsides. Those are rings. Those are carbons that are taking a cyclical shape. Those are cyclo groups. And whenever that happens, that increases the organic nature of the compound, which somewhat increases the non-polar piece of the compound. So if I had to compare beta carotene to lycopene, then it's going to be the story that beta carotene is more organic and more non-polar in nature. Lycopene is a very straight molecule, absolutely. Lycopene is a very organic molecule, absolutely. But lycopene here is kind of funny, because lycopene is actually not as polar. And the reason is because the rings of beta carotene are actually going to increase that non-polarity if I had to compare the two structures with each other. Overall, though, both are organic. Overall, both are non-polar. It's just beta carotene is a little bit more so. And the reason is because of those big, bulky, organic-y, carbon-based rings that happen on the outside. For the most part, the rest of the molecule is the same. For the most part, as far as the carbon chains go, the double bonds go, all of the things that happen in the middle, very, very similar, almost identical. Beta carotene's got 40 carbons. Lycopene's got 40 carbons. They have different number of hydrogens, but 40 carbons are still at play. There's no major differences between the two except for the big rings on the outside extremities. All right. So that's why beta carotene's also going to come out. We got to deal with that. We got to separate that out. Notice part of your lab procedure is probably going to say use water to wash the extract. And the reason for that is because if you have any type of polar pieces that are still remaining, or if you have acetone because your lab directions have told you to use acetone, if that is still present, water can actually go in and play with acetone and help remove that from the organic solvent that you are after. So that is why a water wash is often required. We're just helping ensure that all of those polar pieces are going to be out so we don't have to worry with them in the next step. If you've got a lab book that gives you lab directions on using low boiling point ether, the reason that low boiling point ether is used is because, oh my God, heat can destroy the product, right? So if you did regular boiling point ether, then you're going to have to heat this up on a hot plate and you're going to have to drive it off because we want that solvent to go away. And I don't want to deal with that. I don't want to put it on heat. I don't want to destroy my lycopene if that's what I'm using. So that is why they will often say low boiling point ether, please, because it does come in two versions, low boiling point and regular boiling point, or high boiling point sometimes. The low boiling point normally boils off anywhere between 30 to, I believe, 50 or 60 degrees Celsius. So pretty much room temperature, this thing can go off and evaporate on its own without any help, and no heat is going to be required to drive that off. So that's why we prefer that. If you've made a mistake and you used high boiling point ether instead, then you are going to have to put it on a hot plate. You're going to have to drive it off. It's not going to go off as quickly, and that heat can destroy your product. So be forewarned, you want the low boiling point ether, the one that says like 30 degrees to 60 degree-ish or so forth, somewhere in that range. Another part of your lab procedure is going to ask you to use potassium carbonate. And the reason for that, potassium carbonate is a base. And you've made a solution of it, and you're going to add that solution to your extraction. It's going to mix in, and the purpose of the potassium carbonate is to remove any of the extra acid that might be present in your extraction solvent. We don't want those acids there. We want them removed. Those acids can linger in the organic piece, and we really don't want those acids or a strange, weird pH level in that organic layer. So we need to get those out of there so that way it doesn't cause us problems with the molecule. So the way that we do that is that we neutralize them. So water and potassium carbonate is going to be mixed together. That's then going to go into your extraction solvent, and that little potassium carbonate, which is a base, will look at these acids if they are there, and they're going to go kill, 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 and they just neutralize each other out. And because of that, it might generate a little bit of heat, or you might see a little bit of bubble that happens because the carbonates will tend to break down and they will eventually go to CO2 sometimes, which is carbon dioxide gas. So if you do this in a separatory funnel and you add your potassium carbonate and you see a little bit of fizziness, if you see some bubbles that get formed, that is why those are there. And it's because that CO2 is getting generated and it's getting liberated, and visually you can see that happen. All right. So that's why we do potassium carbonate. After the extraction takes place, they will tell you to take your beaker with that extraction, and you're just going to let this stuff evaporate, and you will be left over with a residue. And that residue is okay. That's fine. Keep it in the dark. Don't let light hit it, right? I mean, we already know the story there. But that residue is going to have to be reconstituted. And the reason for drying it completely is because we want to somewhat control the volume here. We don't want too much volume because that can cause a problem in the little tiny column that I have made with a transfer pipette. So when we control the volume, how do we do that? Well, the best thing is to use something like a micro pipette, right? Of course it is. So what will happen is that I will let this just naturally evaporate. I'll come back to it maybe on a different day or maybe later up in the day if I've got nothing else to do or nowhere else to be. And I'm going to look down at my beaker, and all of that liquid's going to be gone, and I'm going to see just some crust, some reddish, orangey looking crust that's going to be there. So I'm going to take my solvent, and it's going to say, in this case, in both editions, it does say hexanes. It's going to say take hexanes, and you're going to add a certain amount of hexanes to your solid residue and reconstitute it, which means dissolve it. You're going to dissolve it again. Hexanes does evaporate. So if you're very slow with this step, you're going to turn around and that hexanes is going to be gone too. So you're just going to add more hexanes if that happens. All right. It is okay to go over a little bit. And the reason that I say that is because it probably will evaporate some. And by the time you get ready to use it, then you're still going to have liquid left over, and it's not going to ruin anything. But you do not want a lot of volume. All right. If you've got more than like 2 milliliters, absolutely not. That's going to be a problem. That's going to be an issue for you. So what will happen is that you're going to take your column that you have prepared, and you're going to add your extraction to it that has been reconstituted. But before you do that, you're going to take hexanes, because hexanes will be the mobile phase in the very beginning. And hexanes is going to go into the column, and it's going to through, and it's going to drip, 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 drip out the end. Great. That's what we want it to do. When you hit your column with hexanes, your column is now wet. And you cannot, I repeat, cannot let it go dry. If you do, that is when cracks happen. That's when voids happen in your column. This is going to be a big, big problem for you. So when you hit it with hexanes, and when that column goes wet, you need to ensure that it stays wet for the entire process from here on out. Do not let it run dry. That's very, very important. And you know who you are if you're not going to do it and you're not going to listen to me. So this hexane layer will eventually seep down into the column. You're going to wait until the hexane layer gets right on top of that sand. When that hexane goes into that sand layer, that is great. So what will happen next is that you will insert your extraction. That orangey reddish solution that you have just now generated, we want to inject that into the column, but we want to inject it the proper way, and we want it all to go in somewhat at one time. By allowing the hexanes to pretty much completely go under, and then adding your extraction on top of that, you are helping ensure that things do not get diluted and things get included in the column over a course of time. We do not want that to happen. After your extraction goes in, you're then going to wait. You're going to allow your extraction to go fully under. And when that extraction fully goes under, you're then going to add hexanes again. That is your mobile phase. Hexanes will begin to push your sample through the column. And visually, you will be able to see what happens. One of the things that goes on in the beginning is that your yellow band will form first. And the reason is that the yellow band is actually the beta carotene. It's yellow because it's very faint. There's not a lot of it. It's not going to be orange like a carrot, but it's still there. It still shows up, and it is colored, but to your eyeballs, it will look yellowish in nature. That is going to be somewhat the beta carotene that's going to be present in that sample because you extracted that as well with the help of the hexanes that you used, or pet ether that you used. You need to visually watch it. And the reason that the yellow color will travel to the bottom of this column first is because of the structure of beta carotene. Keep in mind, hexanes is totally non-polar. And if I go back to the structures, which one is more non-polar? Ding ding! It's beta carotene! So that's why beta carotene grabs onto the hexanes and it enjoys the ride that hexanes is providing. So it will travel through the column faster, and you'll see the yellow band go quicker through the column. And traditionally, yellow is the very first color that you'll see, and that is why. That's your beta carotene. Lycopene is nonpolar. Lycopene grabs the hexanes. Lycopene will travel. Lycopene, which is going to be a reddish, orangey looking band, will begin to show up. Absolutely, it will. It'll be there. But the problem is that it might just not travel as fast, but it will slowly start to move. When the yellow approaches the bottom of the column, you're then going to take a test tube, and that test tube you're going to hold up underneath that column that you've made, and you are going to capture all of the beta carotene that comes out first. Your orangey layer will still be there. Your orangey layer will still be on top. It's not came out yet because it doesn't relate to hexanes that close. I mean, they get along, but not like that. They're not BFFs. When the yellow fully comes out, that is great. That's what we want. We now have the orange layer that's still there, and that will begin to move as well. And when it begins to move, it'll get lower and lower. But something's got to help it. What helps it? Well, if I continue to use hexanes, it's not going to move. So when the yellow comes out and you've captured that and you feel good about it, good for you, good job, pat on the back. Then you're going to go for another round. You're going to allow this mobile phase that's currently in the column, you're going to allow that to go under the sand layer. When it goes under the sand layer and you've already collected that yellow color and only the red remains, you need to push the red out. You'll push the red out by using a mix, and that mix is going to be a 10% acetone hexane mix. That's what that will be. So what's happening now is that you're changing the polarity. And that lycopene is going to look at that mixture and it's going to go, oh, you got prettier. I think I like you now. And then lycopene is going to hang on to the mobile phase and it's going to rush out of the column. That's great news. Because again, down here at the bottom, I'm going to have a test tube. And when that orangey layer gets ready to come out, I'm going to switch my tubes, and then I'll be able to capture that orange solution. You could see a little bit of remnant that will happen inside of the column. You could see a little bit of yellowish that still remains. It's not a big deal. You're after the red color. You're after that orange color. That is what's going to be ran on UV. It's not going to be the yellow at all. So who cares? But this is what you want as far as the instrument goes. And the analysis piece goes. That's what we're after. Right? Alumina is going to be used as the stationary phase in the column. So when you packed it, aluminum is typically kind of the go-to. It's pretty pricey, actually, though. Alumina and silica is about $1 a gram, if not more, maybe $5 a gram, depending on the year. And Al2O3 is the structure for alumina. Alumina is very polar. And it's one of the reasons that we're using it in this experiment, because lycopene is nonpolar. It actually doesn't like the alumina. If something else is better for it, it's going to definitely go there, because it doesn't get along with alumina at all. And that is why it starts to move through without hardly any help, because it hates alumina. And you know, beta carotene actually has a bigger attitude, because beta carotene is going to come in and it's going to be like, God, alumina, I hate you. And then it kind of runs through the column without an issue. So that's perfectly fine. Not a big deal. I mean, it's there, but that is why alumina or silica is often used for these types of separations. So when that new mobile phase comes in and that lycopene's like, oh God, yeah, I like that way better. Get me out of this polar alumina state, please, because I'm non-polar and that thing's polar and I don't get along with it and we don't see eye to eye on anything. So that is the reason that alumina is going to be used there. Alumina would attract more polar molecules. And, you know, again, lycopene is not polar. But out of the two choices, lycopene and beta carotene is more non-polar than lycopene is. So beta carotene hates the alumina more than lycopene does, and hence beta carotene will travel through the column quicker than the lycopene will. So that's kind of how the chemistries are going on, and that's what begins to happen in your separation technique. Here's a picture of what people normally end up seeing. The yellow color here is pretty strong. Yours might not be that type of color. It might be very faint, and if so, that's okay. Again, it's not a big deal. That's really not the important piece anyway. The important piece is going to be your reddish orangey type of color. As far as chromatography goes, lycopene does oxidize. And when you get that lycopene extraction, it is now in the presence of light energy and so forth. So you really do want to analyze it as soon as you extract it. That is very, very important. The reason for that is because that lycopene can flip, and we are after the trans product. That is what we want here. So the longer I let this sit, the longer this has as far as chances go of going into the cis formation. And that's going to be bad news for my grade, and that's bad news for the extraction, and that's bad news for the quality. So I really do want to be prepared to run UV immediately after the fact. The UVs will probably already be on for you. They will tell you to scan it in the realm of 400 to 600 nanometers. We don't want a fixed run. We want a scan run. And a scan will mean that it will go from 400, 401, 402, 403, 404, 405, 406, and blah, blah, blah. So scan it. That's going to be the option in the software that you want to pick. And then in addition to that, you want to use a quartz cuvette. And the reason that you need a quartz cuvette is because this is visible, right? And plastic would have been okay. But the problem is that it's organic solvents, and organics will eat the plastic. So you could have used glass. We do have them, just not very many. And quartz is acceptable for everything. They're just so expensive. So use quartz cuvettes when you begin to analyze your samples on the UV. The blank has got to be a mix of the acetone and the hexanes. This mix is what gave you the lycopene extraction, right? You used a 10% acetone hexane mix to flush out that red color. That is what that red color is going to be in solvent-wise. So that is what you want to blank with, a 10% mix of acetone and hexanes. So hopefully you made a little extra. Hopefully you have some still around. Hopefully it didn't take, however much that you made. Typically people do 10 milliliters. But if you didn't use it all, good news. You'll need it for the blank. So fill a quartz cuvette with your solvent and fill a quartz cuvette with your sample. The goal here is to try to get at least 50% trans lycopene. If you did not get 60% trans lycopene, then or 50% trans lycopene, then the problem here is that you probably had a bad extraction. You were lazy about it. You were sloppy about it. You took too long. You used too much heat. You exposed it to light too long. Most of the consumer products are higher than 50% based on what we've seen before in the past. So if you do go below 50, it's really on you. It's not on the manufacturing side, but it's on you. When you scan the lycopene samples, this is kind of what you see, hopefully. The issue here, though, is that this is somewhat scaled in a different way. When you scan, notice it says 360 here. When you scan, it's going to tell you to start at 400. So a lot of that below it is going to be cut off in a way, and you won't really see that initial type of busyness that happens with the UV spectra. But you'll find the two humps over on the right-hand side. The two humps here are 471 and 502. This is what's also stated in your lab procedure if you read the background information. These are going to be two areas of importance because this is how we calculate how much trans is still left in your sample. What they tell you to do is they'll tell you to scan 400 to 600, and there it is. And then they will say, using a ruler, blah, 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 blah. All right, so if we use a ruler, they're going to tell us to draw a line here at the very bottom where the trough is at, right? So right in here, that's where the ruler and that's where that line should go. And they're going to tell me to measure the height of that peak and the height of that peak. And we're going to measure that height in centimeters. So when we measure that height in centimeters, we're going to have to do a slight calculation on this thing. And what we'll do is the equation that looks like this, over here to the left-hand side. So it's going to tell you to take B, divide it by A, minus 0.40. And then we're going to divide by 0.40. And we'll multiply by 100 to get it into a percentage. A is going to be the larger height, so the tallest. And B will be the shorter one. So when I take a ruler and I measure the heights, let's say that this one is 8 centimeters perfectly. And then from that dotted line up to the top of that hill, let's say that this is 6 centimeters perfectly. So to solve this equation, I'm going to take 6, divide it by 8, and I'm going to subtract 0.4. That needs to happen on top. I'm going to divide by 0.4, and then I'm going to multiply by 100. So if I pull up the calculator and we work through this equation or this math, just to make sure we're all on the same page, then we'll see what kind of answer we come up with. All right, so 6 divided by 8 equals 0.75. I'm going to subtract 0.4. That gives me 0.35. Then I'm going to divide that by 0.4 coming from the bottom equal. That gives me that. And then I will multiply by 100 in order to get a percentage, and that's 87.5%. So that means, hey, you know, I did a pretty good job with these made-up numbers. I mean, you know, typically 90% or higher is great. That is good quality lycopene. I extracted it from a tomato paste product, and then I analyzed it. I ran it. It looks like it's 87.5%. Whew, thank goodness. Because the threshold here was 50%. And in your data sheet, there's going to be a question, and it will say, was your calculation greater than 50%? And if that answer is a no, you're going to see a whopper of a point total that gets subtracted. And the reason for that is because that is kind of giving me an insight to your technique. Was it sloppy? Were you lazy about it? Did you not do a very good extraction? Did you not run it the right way? Did you do things as far as the steps and the procedure go that makes sense? That's a number that we often go by. And if you have a number lower than 50%, you have significantly messed up in some form or fashion. And we need to figure out what you did. And by doing that, that means you're going to have to repeat the lab unless you want that major point deduction taken off of your total. So that is how we do the calculation at the end of the experiment. The data sheet's going to ask for other things. There's going to be some questions. It's going to ask you to think about stuff. Why'd you do this? Why'd you do that? What would happen if we do this instead? But I think that based on the lecture videos that you've received for the lab, that you will be able to answer a lot, if not all of those questions on what we've discussed and what we've talked about. So in the lab, I hope that you had luck, or I hope that you will be lucky, depending on when you watch this. And if you got questions, please let us know. Especially if it's your first time doing chromatography, we will be there with you to make sure that you're doing it the proper way. You just need to ask us for help, and we'll kind of be there, and we'll show you when to add things and how to add things the proper way and so forth. So that's the story with Lycopene, folks. Again, just a general intro, get to know me chromatography experiment. And hopefully that will get your mindset around the rest of the semester. And the reason I say that is because separation is going to continue to take place. But that separation is going to take place in a column that you will not be able to see. And that separation will involve compounds that will not have a visual color like Lycopene does. So I think by watching it firsthand, it gives you a better grasp of what's getting ready to happen for the rest of the semester. So if you got questions, please reach out. And again, good luck on the assignment. Good luck on the exercise. And until the next laboratory lecture video, we'll talk again.